Okay, this is the comparison test. And there's different ones. There's compare tests, plural. There's direct comparison, and then there's limit comparison. And limit comparison is stronger, actually. But to kind of understand how a comparison test works, it's best to start with direct comparison. And the important thing, which I've highlighted right here, is, and a lot of students, unfortunately, a lot of students, they misunderstand this part. And that is, in my opinion, is this part right here. You're supposed to compare the terms, not the series. Okay, so you would say, so by this, I mean, this is what you're looking at right here. Okay, this is comparing the terms in the series, not the actual series. Okay, not saying, oh, the series A sub n is less than or equal to the series, the summation B sub n. No, you don't do it that way. Just compare the terms. Okay, so here's how direct comparison works. Let's run through this first one. So if you have a series B sub n, okay, and also another thing that you need is all the terms in the series must be positive to apply this. Okay, so this is assuming everything here is assuming that all the terms in the series are positive, and also in the series of A sub n and in the series B sub n. Okay, so the idea is this. Let's say that you want to know what happens with the series A sub n. And you know that this series converges, and you know that these terms, that the A sub n terms are less than or equal to the B sub n terms. Well, then it follows that the A sub n series converges also. Okay, because these are less than that. So if this one converges, then this one's kind of forced to converge as well to something less than or equal to whatever this one converges to. Okay, and then likewise, if you have a series that diverges, and then you have your A sub n or has bigger terms, then it's also going to diverge. Okay, then this is for all terms. This is all terms. Okay, so this is direct comparison and how that works. Let's do a couple of examples of that, but before we do that, I want to point out that there's two different, these are typically what you're going to compare with. So you have a series, and you want to know if it converges. Sometimes you can compare it to a p-series in this way, this or this, and sometimes you can compare it with a geometric series. So like, for example, you have a series A sub n, and you compare that with a p-series, and you have this p-series that converges, and then your A sub n terms are less than or equal to all the terms in the p-series. Okay, then your A sub n term is going to converge. Or if you have an A sub n term where the terms are greater than or equal to all the terms in a p-series, and that p-series is in this situation where it diverges, and your A sub n terms are larger, then it's also going to diverge. Okay, and then likewise, with the geometric series. So those are conditions for when they converge and diverge. Okay, so let's do an example or two before we get to the limit comparison. And also, actually, let's talk about the, okay, we have this right here. So this is just rehashing what we went over. So you have two series, and B sub n is known to converge, the B sub n series. And A sub n is greater than B sub n. Okay, so this is a different situation where, this one converges, but these terms are greater than. So that really means that in that situation, you can't really tell what's going to happen, because you have, this converges, but then these are bigger than. So that doesn't. So it only applies with the A sub n terms are less than or equal to. If the B sub n converges, you can only say something about if the A sub n terms are less than or equal to. And here it's saying they're not less than, they're greater than. So that's like what? So that means you can't say anything, unfortunately. So that's the answer there. On the other hand, if your terms are less than the B sub n and this one converges, then it's going to converge by the comparison test right here. It'll converge by the comparison test. Okay, so this is the proper way to do it. Here you can't sometimes people make the mistake of saying, oh, well, this is greater than some other series, so therefore I have to diverge, but that's not necessarily the case, okay, because B sub n converges. It's great. The terms are greater than a convergent series, okay, so that doesn't mean that it's going to diverge because it's greater than. I mean, you can have lots of different values of p that are greater than 1, and then they both converge, right? Or they're different from each other, and so one's going to be less than another. Okay, let's look at number 2, and here we know that the series B sub n diverges, and here A sub n is greater than B sub n. Okay, so if this diverges and you have something bigger, then it's also has to diverge. Okay, so that's going to be this case right here. And then this one right here diverges, but your terms are less than, then we can't really say anything. Okay. So those are different situations that come up. Okay. Oh, yeah. Okay, number 3, determine whether the series converges or diverges. Okay, so here you have a to the n over 7 plus 13 to the n. Okay, so here if you see things raised to powers, then a good candidate would be to compare it with would be the geometric series. And in this case, now a lot of times what you should look at, okay, is look what are the biggest term. If you have a fraction, what's the biggest term in the numerator or the biggest term in the denominator, and just focus on those two. Ignore everything else. If you just ignored this 7 plus, you'd have 8 over 13 quantity to raise to the nth power. Okay, 8 to the nth over 13 to the n is equal to 8 over 13 to the n. Okay, and this would be your r there. Okay, now because we added something in the denominator, we know that this is less than 8 to the n over 13 to the n. Okay. So what happens here is this denominator is smaller than that denominator. This is bigger because you're adding a 7, which just doesn't have the 7. So this is smaller, which means that the overall fraction is, this one is larger than this one. Okay, so we could also say that right there. And then in this case, if you look back up at the direct comparison, okay, our A sub n's this is the A sub n, and this is B sub n. Okay, you're comparing the terms. You're not comparing a series. You're not comparing this series and this series. You're comparing the terms. Okay, if A sub n is this, B sub n is that, A sub n is this, B sub n. We also know that if you take these terms, this converge or diverge. This one converges because 8 over 13 is less than 1. Okay, because 13 is more than 8, so that's less than 1. Okay, and so that means that this series right here, I'll just say series. I don't want to write the whole thing back down again. So series converges by comparison test. Okay, here's number 4. Let's take a look at that one. And what you do there. So like I said, a good place to always start here is, like I said, is to focus on highest ordered terms, largest terms. And by that, I mean the largest term in the numerator and the largest term in the denominator. Of course, as n is going up to infinity, as n is growing larger and larger. Okay, because like when you're starting out, the n squared is going to be less than 9, right? But then soon, as you start going off to infinity, this overtakes the 9 and dwarfs the 9. Okay, so you just look at this right here. And that is 8 over n, okay? So what do we know about this series here? What do we know? Is this going to converge or diverge?
It will diverge.
Yes, it diverges.
Yeah, I had to look back at my notes. I have a hard time remembering these.
Yeah, this is a p series, and p is equal to 1, which is less than or equal to 1. Okay, so it's right here again. It's the p series. It converges if p is greater than 1. It diverges if p is less than or equal to 1. And so p is 1, so it diverges. Now, unfortunately, if you look at this one, this is actually less than 8 over n. Okay, this is less than. So this is less than a series that diverges. So direct comparison doesn't work. We could actually you could make direct comparison work. You could it doesn't work like when it's like this, but you could do something like maybe just have a 1 over n instead. Then definitely this is bigger than that, right? For once you get past a certain point. So you could use direct comparison there. Okay, but so you could like make it work like that, because this series right here also diverges. Okay, so you could make direct comparison work that way, but it's a lot easier if you use the limit comparison here. Okay, so I ran out of space, darn it. I'll just use, it's easier if you use limit comparison. I won't do it on this problem, but I'll do it on this problem here. I'll use limit comparison. Okay, so if you focus on the largest terms, in this case, the the biggest order, it's n squared and n to the fourth, right? Which reduces to 1 over n squared. Okay, so that's what you focus on. Now, let me show you how direct comparison works. We're going to use direct comparison and compare this series with, or compare these terms with those terms, 1 over n squared. Okay, so limit comparison. You take, if you have limit is n goes to infinity of a sub n over b sub n, that's what you're looking at, okay? If that's between 0 and infinity, if that's some value between 0 and infinity, then they both converge or diverge together. So you don't have to worry about which one's larger or which one's smaller. They're just both going to do the same thing if you have this situation right here. Okay, if this could also be 0 or this could be infinity, in which case they could do different things. But they still might do the same, but you know, doesn't necessarily. Okay, so what we're going to do is limit comparison. And we'll let the a sub n's be these. And b sub n be this. Okay, so the limit as n goes to infinity of a sub n over b sub n. That's what you're looking at, and you're looking to that for that to be a finite number. Okay, so here's our a sub n, here's our b sub n right there. Okay, now this one, you're basically taking off this fraction and dividing by this other fraction. So you invert this one and multiply that on the top. So you get that. And if you distribute that in, you have n to the fourth plus n cubed plus 8n squared over n to the fourth plus n squared. Okay, what's that limit going to be?
It's just going to infinity. So it'd be.
It's going to be 1 because you just look at
the highest one.
Yeah, the highest order term. They dwarf everything else. Everything else is insignificant. And there you go. Another way to look at it would be if you were to multiply the numerator and denominator by 1 over n to the fourth. This would be 1 plus 1 over n plus 8 over n squared. And then this would be 1 plus 1 over n squared. And that's just going to be 1. Because all of these, every single one of those just goes to 0. Okay, so you just got, everyone goes to 0. Okay, so you're just going to get 1. And that, and 1, you don't have to get 1. You got any number between 0 and infinity works. We know this series right here. What does this do? Does it converge or diverge?
It converges.
Yes. Okay, so it's a P series. And P is equal to 2, which is greater than 1. So it converges. So therefore, this series here converges. by limit comparison. Great. Okay, let's move on to the next exercise. Number 6, unless there's any questions. Okay, so number 6. Here we have, so this part right here looks kind of what I showed you at the beginning of class, except there's no n right here. So what happens here, you might notice if you take 1 plus 3 over n to the 4th power, what happens is the n gets larger and larger. This goes to infinity.
And then that just goes to 0.
Yeah, this is going to go to 0, and you'll end up with 1 to the 4th, which is 1, right?
Mm-hmm.
Okay, so that's good to know. That's to 1, and also if you had just e to the negative n, would that converge or diverge? That's the same as 1 over e to the n. E is about 2.7 something, right? So
Yeah.
1 over e will be less than 1, and that's going to converge. Okay, so what I'm going to do then, so this part we know, if you have something like this, so this part right here just goes to 1. This one converges, just by itself would converge. Then what I'm going to do is I'm going to make a sub n be these guys here. And I'm going to make b sub n just equal to e to the negative n, because we know this series converges. And then take the limit as n goes to infinity of a sub n over b sub n. So that's 1 plus 3 over n to the 4th, e to the negative n, all over e to the negative n. And this is just going to be 1, right? Because this and this are just going to cancel. And then this goes to 1, like we said. Okay, so since this converges, then this original series converges by limit comparison. Okay, any questions before I move on? Okay, let's look at number 7. So here we have 32 n factorial over n to the n. Whoa. So what I'm going to do is I'm going to set a sub n equal to these terms right here. And in this situation, it helps a little bit to multiply things out. So we have 32 times n. So n factorial is n times n minus 1 times n minus 2 times n minus 3 times 2 times 1. That's what n factorial is. Now, n to the n would be n times n times n times n times n times n. All n's, right? Okay, so what I'm going to do, in this case, it might look a little bit weird, is I know that these are going to cancel, right? And then I know that this term's less than that one. that one's less than that, that's less than that, and so on. So what I'm going to do is since I know this is less than that, that's all these terms are less than, I'm going to throw them all out, and I'm going to say, okay, 32 times 2 times 1 over n times n. Okay, so I'm going to throw out basically all of that right there. I know all of this is less than 1, right? All that, because this is less than 1, that's less than 1. So we have a whole bunch of stuff. And there's exactly the same number of terms up here as there are down here, which is n minus 2, whatever n is. I'm going to throw all those out. So this is less than 1. So I get this. Now, for the first term, obviously, we're not going to have more than one term, but it doesn't really matter. This will converge if I can show that going from 100 to so on or whatever, if I can show that this converges, then that proves that this converges, because you can throw out how many ever finite terms you want. Okay, so that's why this will work right here. Okay, what do we know about this series here? If we take 64 over n squared, is that going to converge or diverge?
It converges.
Yes, great. Because it's a p series, and p is equal to 2, which is not greater than equal to, it's greater than 1. Okay, so that will converge. So here we have these terms right here are less than these terms in this other series that converges. Therefore, converges by direct comparison. Okay. So let's look at number 8. Determine whether the series converges or diverges. And first of all, if you see a sine or cosine or whatever, then you might think, well, what happens as n goes to infinity? Does this even go to 0? And the answer is yes, because as n goes to infinity, 3 over n is going to 0. Sine 0 is 0, right? Okay, so converge or diverge. Now, maybe what we can compare, okay, so if you see, you've heard of this inequality, right? You remember this one? That's equal to 1. Remember that? Okay, well, if not, then
a little bit.
a little bit. Okay, so we can apply. Okay, so if you don't remember, that's fine. But you can look. You can just what's it? L'Hopital's rule. Wait, what am I doing? Limit as x goes to 0 of cosine x. So you take the derivative of sine as cosine, and the derivative of x is 1. And then as x goes to 0, cosine of 0 is 1. So that limit is going to be 1. Okay? So that's one way to show that. Okay, now you don't have an x, but you have 3 over n, and as n goes to infinity, 3 over n is going to 0. So it's basically the same as this. It's the same concept right here. This is what's going to happen. So what I'm going to do, okay, this is my a sub n, is 5 sine of 3 over n. and I'm going to make Bn just plain old 3 over n. And then take the limit of an over bn. Okay, so the numerator is going to be this, 5 sine of 3 over n, and b sub n is 3 over n. Because of this part, as n goes to infinity, and this goes to 0, and this goes to 0 at the same rate because they're the same. This is going to 1, so I'm going to get 5. Okay, so I have 5. And 5 is certainly between 0 and infinity. Okay, now, if I look at this right here, the series with those terms, does that converge or diverge?
That diverges.
Yes, this one diverges. It's the p series with p equal to 1, and it's the harmonic series, it's diverges, so the answer is diverges. So that means that this series here diverges by the limit comparison.